I did not do very much. Well, I did a lot of stuff, but I did nothing for here, so I was kind of negligent in a way. But I wanted to go back and look at some problems that we have in some of the stuff that they discussed in chapter 9. We really, or yeah, chapter 9, we really didn't get a chance to do. So I'm gonna work on some of the other approaches to solving Laplace equations. So let's just do that now. This is a review of sorts of the, what you would do in EET 4450, but I want to go through some of this stuff. This is the homework assignment from 4450, but some of these questions that are in here, they didn't cover adequately in chapter 9, and I wanted to go through and work on a few of these. So this is looking at some types of problems from the homework assignment in EET 4450. So this one right here. Okay, so this is a kind of question that you might see, and you might have to solve. And we did not work on this type of question. Okay, we didn't try to solve this one. All right, so you've got your Laplace sheet, and you see here it's a term squared in the denominator, and we didn't talk about this type. So this is one where you have to so 4a, so it's 1 over s times s plus 2 quantities squared. Well, that is equal to a over s plus b over s plus 2 plus c over s plus 2 quantities squared. That's the expansion of that. Okay? And that's easy for the a term and for the c term, but for the b term, it's not. So you have to expand this as either, like it said, it's a. So I'm combining the denominators on the right side. So it's a times s plus 2 quantities squared plus b times s plus 2 quantity, just one, plus c times s. And that's equal to 1. Okay? Now, does everybody understand that that's making common denominators on the right and on the left, and now you just cancel the denominators out, and this is what you get? So what is A, B, and C? Well, if I let S equal 0, I very quickly can cancel out this term and this term, and I just have A times 0 plus 2 squared, or 2 squared, is equal to 1. A is equal to what? 1/4. And I've got the A term. The C term is not so bad either, because I let S equal what? Minus 2. That makes sense? Okay. So far, I'm good. But the B term is not so easy. That makes sense? So how do you get the B term? Well, that's the That's the point of what I'm asking you now. How do you get the B term? All right, let's get the C term. Let us equal minus 2. 1 is equal to what? This term drops out, this term drops out. C times minus 2 is equal to 1. C is equal to what? Minus 1/2. You're good. But the B term is a problem. So the B term becomes an issue. So let's look at this for a second. And I've got A times S plus 2 quantity squared plus B times S plus 2 plus CS equal to 1. Now, the book that I showed you, the one from Illinois that I talked to you about, says take the derivative, okay, of S, and you can find it that way. You can get it down, and you can crunch this down. So now I know A and I know C, but I don't know B. You can do that. You can take the derivative of S, and you'll find it, okay? But the other way is called the balancing act, okay? It's called the balancing act for a reason. Okay, if you have something with S or S squared and you drive S to a large number, those terms tend to dominate over the other terms. So if you have a balancing act of S squareds on the left, you have to have a balancing of S squareds on the right, okay? So let's look at that. So that's A times S squared plus 4S plus 4 plus B times S squared plus 2S plus CS equals 1. So let's just look at the squared terms. A on the balancing act, I put a little colon there. The balancing act for the S squared terms, A plus B equals 1. Does everybody see that? The S1 term, 4A plus 2B plus C equals 1. Now, you can use either of these. You can use this one or you can use this one. Sometimes you have to use them both. And there's the S to the 0 term, which would be 4A equals 1, or A equals 1/4. But I would, in this case, I already know A, I do not know B. I'll just use this one and be done with it, and scratch this one and scratch this one. Sometimes you have to use all three of these. All right? So what would be B? Is a fourth. B is what? 3/4, right? 1/4 plus 3/4 equals 1. Questions about that? So now I can rewrite. What is my answer to this question for A? Well, it's A over S over R just 1/4. So my F of T is equal to what? 1/4, which is my A term, plus 3/4, 1 over S plus 2, or E to the minus 2t, plus, minus minus 1/2 t e to the minus 2t. Does everybody see that t, that's rule number what? 23. This is rule number 23. Okay. Now, what does this look like? What does this function, what does this function actually look like if you were to graph it? Okay, so you have a graph of a fourth. .25, okay, plus e to the minus 2t, 3/4. So it starts here at 3/4, e to the minus 2t, so it starts down like this. Starts at 3/4 and goes down. And minus a half t e to the minus 2t, which is this times another function, which would be this function right here, which is this kind of a function times this type of a function, which would give you a what? You multiply this times this, what do you get? Like that. So you get this plus this plus this. So you get whatever. You add those three together and you got your final answer. Okay? But that's the right answer. That's how that's done. Now, this can get, as they say, this can get very, 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 very difficult. You can get 4, 5 variables. Okay? I promise you I will not let that happen. All right? But we didn't talk about this type of question in chapter 9. But you should know that this is how you solve this type of question. It's called a balancing act. Or if you want, you can take the derivative of s and then find the answer that way. Take the derivative, see what plops out, take the second derivative, see what plops out. It does the same thing. It gives you the same answers. If you don't believe me, try it that way as well. So this is the preferred way of doing this question, the balancing act. So when you see something like this, don't panic, because you can't find it just by let s equal 0, let s equal minus 2. You can't find the b term. It's just not going to happen. You got to turn to this guy in order to get the final values. Any questions about that? Does that make sense? Good. Because that'll happen. This is not like we're just going through this for our health. This little puppy will perk its head up, and you will have to work these as well as the other ones. Okay? So we didn't touch this one in chapter. He did not have a problem like this in chapter 9. I don't know why, but he didn't. But you probably will have one like this somewhere. It'll pop up in chapter 10 or someplace. So be aware of that. Okay, let's see if we got another one down here someplace. But this is, oh yeah, this, as they say, they get worse. Okay? They get worse. This one, E. Everybody see that one? How would you do E? It's 2 times s plus 2 times s plus 5 quantity squared all over s plus 1 times s squared plus 4 quantity squared equals what? I got that all messed up, but it's like this, s squared plus 4 quantity squared. Okay? So that's how you expand this kind of a question, okay? So how would you find these variables? You're going to look and see if you can find something. So let's expand this. Okay, this is a lot more difficult than the other one, but it's the same principle. It's 2 times s plus 2 times s plus 5 quantity squared is equal to a times what? Squared? Because you got to s squared plus 4 quantity squared, because you got to do that whole thing, plus b times s plus 2 times s squared plus 4, plus c times s plus 2, right? Yes, sir.
Having this a plus
S plus 1. I got it. Thank you. Thanks. All right, so I've got this whole mess. So now, how do I find my a term? Yeah. Yep. Let's say x equals minus 1. So what is a? So, okay, this is a 2 here. It's a 2. Okay, so that s equals minus 1. So this is minus 1 plus, okay, it's 2 times minus 1 plus 2 is 1 times 4 squared is equal to a times minus 1 squared plus 4r 5 squared. Okay. What is a? So 2 times 16, 32. Is equal to 32 over 25, right? Right? This is hard. This is not an easy one. Is that right? Let s equal minus 1, minus 1 plus 2, minus minus 1 plus 4. This is s squared s plus 5. No, it's 2 times 1 times 4 squared. 4 squared is equal to a times 1 plus 5 squared. Yeah, that's right. Okay, that's a. What's b? We don't know. What's c? Let s equal what? 2j, right? Right? If you let s equals 2j, what is c? What is c? This is not easy, okay, but it's doable, all right? So what is it? Two plus 2j. At this point in time, what you can do is the following. You've got A, okay? Instead of trying to go get C directly, what you can do is you can do the following. You can say, okay, this point in time, instead of doing this, you can say, all right, now you look at the A terms, the B terms, and the C terms, and you say, okay, so you've got 2 times s plus 2 times s plus 5 quantity squared. This one's not easy. Plus 10s plus 25 is equal to a times this, and then b, and then you got c. And then you've got your a term, then you can get your b and your c term by looking at the balancing act of these two. I'm not going to do this one. You'll never have one this hard, but that's how you do it. That's one way of doing it, okay? I'm not going to do it. It's just too much. But that's how you do it. I bit off more than I could chew there. Let's do F. This one's a little easier. S squared minus 1 over s squared plus 1 quantity squared is equal to what? A over s squared plus 1 plus b over s squared plus 1 quantity squared. So with this one, you can say, all right, let s equal I, and then that plops out this one. Or you can do it just like this. You can say s squared minus 1 is equal to a times s squared plus 1 plus b. Okay? Now, in this case, we can say we just go straight to the balancing act. Do the balancing act. S to the squared, s to the 1, and s to the 0. All right? So here we have s squared minus 1 is equal to as squared. So one s squared on the left is equal to a s squared on the right, so a is equal to 1. All right? And then there are no s to the 1 terms, so you can get rid of that. On the left, there's a minus 1 is equal to a plus b. There's an a term and there's a b term with without the s, without any s's, there's just that. So if minus 1 is equal to a plus b, b is equal to minus 2. You've got it. So this is one where you can easily go to the balancing act, chuck anything else, and you're done. Sometimes it's easy, sometimes it's not. But this is one where you can effectively go to the balancing act. Now, what's the final answer? Well, it's 1 over s squared plus 1, which is what? Okay, what would be the easiest, what is 1 over s squared plus 1? What is that in terms of time domain? That is sine of 1t, or just sine of t. That's the conversion of that one. What about this squared? Two over s squared plus 1 quantity squared. Anybody see that on the sheet? There's no s in the numerator. That's rule 10 has an s squared minus a squared in the numerator. So it's not rule 10. It's got an a. Rule 9 has an s in the numerator as well. Anybody do a chat GPT of it? I don't know the answer to that one. But you see the process of getting to that point. Sometimes you have to use this balancing act as opposed to other techniques, and you very quickly find the B term. But how then you get that to something meaningful? I was hoping it would be T sine of AT, but that has an S in the numerator. What's that? That is it. That is it. It's yeah, that is it. Rule 23. Very good. E to the minus t. So that's minus 2 t e to the minus t. You're done. Thank you. Very good. Rule 23 it is. Good eye. No, it's not. No, it's not rule 23 because it's a S squared term. Sorry about that. It's not rule 23. I'll tell you what. Anybody finds that, let me know. We'll ask that question, but I don't have the answer to that one. But that gives you an idea how you do these, and I'm not trying to make it sound like it's very hard. This approach breaks this down very quickly, and then you got to be able to find the final solution. Let's do a chat GPT and see what it says. All right, I become a strong believer in chat GPT. Fourier or applause. Minus 2 divided by brother. S squared. I don't know how to do a squared. Let's say S squared,
Just do the up arrow and then a 2.
up arrow and then a 2? Okay.
Yeah.
Thank you. Rotated. Oh, there it is. Squared plus 1. There it is. There it is. They did that. It's t cosine t minus sine t. Okay. So again, don't want to belabor that, but that's how you do it. I won't give you one with that kind of I'll give you one that'll be able, you can be able to solve on the sheet, but that's the truth. This is the way you break these down. Okay. Any questions? Everybody understand how that's done? All right. So let's go to chapter 10. Chapter 10 is where the bulk of our work is, and that's where we're going to have to concentrate on. So let's go to chapter 10. These questions are found, this stuff is found in my EET 4450 class, the homework number 4. So if you want to know where that came from, it came from EET 4450 homework 4. That's where all the heavy lifting, Laplace is in that course, is in that homework section. Okay, so let's go back to our book, chapter 10. And see where we're at, chapter 10. Like I said earlier, I looked through this chapter and I was going to get more involved in it. And last night I said, the heck with it. So I'm But I do want you to understand a few things here before we get too far along. And this is not this one. So this one. Okay, so please, on the back of your sheet or somewhere, write these things down. Okay? So when you see this is, and I'm going to write it on the back of my sheet as well. So when you see an R, it's just an R. Okay? So in the time domain, in the S domain, this is what you have. So this is in the time domain, and then in the S domain. So if you have an R, it's an R. If you have okay, and here's your V and your I and all that kind of stuff. And here you have an inductor, an L, and in the S domain, it is an LS, and then a voltage supply minus to plus of L times I sub L at 0. That is the current when you turn the thing on. At t equals 0, the initial conditions of the current. Okay? With the plus sign down. Okay? So if you have initial conditions with no current in the circuit, what can you do? Drop this out. This goes away. Okay? And what is it for capacitor? C. Now with this one, the plus is up. You got to be careful. The plus is up, and the value is 1 over CS, and the value of the voltage supply is V at 0 over S. Okay? So when we solve a problem now, we use the same techniques as we did in resistive circuits, except for the fact that what? When you're writing a voltage loop, or you're writing mesh equations, or anything that you did, or anything that you've done, instead of this, you write this. Instead of this, you write this. Instead of this, you write this, and you're done. That's it. So if you write these things down and have them in a safe place that you can constantly refer to them, you're in. Now, that's the bulk of chapter 10. Really, it is. All right? Everybody understand why this works this way? It's just to tell you, in one case, to do this, and it's just rote. And it's another case to say that it is why it's this way. All right? And I'm going to give you the nickel answer. Eli the Iceman. Okay? Eli and ice. Anytime you see a derivative of something, what do you write? Excuse me, instead of over here, if you see a derivative of something, what do you write over here? Leo? If you see the derivative of something in this domain, what would you write over here? S. If you see the integral of something over here, what do you write over here? 1 over S. Okay? Does that make sense? Because that This is where all this stuff comes from, right here. So I'm going to write it on the back of my sheet as well, because I'm going to do the exact same thing I want you to do, and that is to be able to do this, because that's the whole secret of this chapter. So we got it. The secret's out. That's all you got to do. All right? So let's go to the end of the chapter. Start looking at what they're asking us to do. All right? Oh, you can do the same thing with current. Now, how many of you want to do a current supply? No, you do not want to do a current supply. If you had to, this is how you would do it, but please don't. If you do this to me, I will probably shoot it down. You get the idea. There'll be 4 or 6 or 8 questions. Most of them will be, here's a circuit and the time domain, give me the value of blah, 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 and the final answer in the time domain. But in order to do that, you got to convert it to the S domain. You got to do the magic of what we just talked about with the Laplace transforms, and then you get it back to something on the sheet, and you bring that sheet answer back to something that you can use. So that's how you do it. So anyway, or your ChatGPT it. And again, you're not going to have ChatGPT with you on a test, but as far as I'm concerned, it gives you a little bit of a head start in some cases of being able to understand how this stuff is working. Okay, so anyway, that's beside the point. So that's all there is to this chapter. It's really an easy chapter. Once you understand this part, once you understand how chapter 9 works, this is really an easy chapter. Okay? So here's a why is this why the heck do they do that? Oh, it's an exponential decay. They put in a voltage supply. Every once in a while they do that, a voltage supply that's an exponential decay. If it's just a regular, like a DC supply, what is it? It's a constant. And you've got to put the over S there. Do not forget that. You cannot forget the constant voltage supply over S. Here's one where they put in a voltage supply of an exponential decay. Why would they ever do that? I don't know. I do not know. Here's one where they have a straight U of T. In other words, that's a DC source, right? So what do you do there? Over S. That's rule number 1. A constant is that same constant over S. All right? And there's your answer. No biggie. That's how it's done. It's exactly how it's done. Everybody understand this problem right here? Because we could go through 10 of these problems and examples, but we need to start working them. And in other words, we need to start playing the game. The game is exactly, you start here, you're given this, and you say, what is the voltage, or what is the current through the inductor? What is the equation for the current through the inductor? Okay, and you all know it because why? Because we've trained you to look at a certain circuit and know the answer, right? But if you did not know that answer, if you forgot chapter 8 of the DC book, or whatever chapter it's in, if you forgot that and your mind turned off and you hadn't remembered that, how would you get it? Right here. What if they throw you a curveball and it's not quite the same thing? What if they have an inductor, you know what I'm saying? What if they threw you a curveball and it doesn't fit your exact style or whatever? Then all of a sudden you're out of luck. But not anymore. Not anymore. You got all the tools you need to do anything you want with every part of it. Okay, that's all you have to do is remember that it's the same circuit exactly that it was before, except now you've got these new things. Okay, now can you, if the if this is 0, can you combine these? And yes, you can. You can do parallel combinations, you can do series combinations, but if you got this thing in there, if you got this part in there, it's just like superposition. You cannot combine things when you've got this kind of a thing in there. So you can't do, like in other words, right here, if they, you follow what I'm saying? You can combine these two as long as what? Initial conditions are 0, because then that drops this puppy out, that drops this puppy out. But if that's in there, if that's physically there, you cannot just combine these two. In other words, I can use my parallel rule to combine these two, except for the fact that if they drop in an initial condition, I can't. So you gotta look. Can I combine? Maybe. You gotta be careful. So they play these games on you, and but okay. So anyway, so you see how this circuit works right here? I want to find the voltage across this resistor. How do I do that? Duh. I gotta go in here and I gotta do all this stuff? No. You gotta do this. Oh well. Did everybody see what's ahead? All right, that's all it is. That's all this is. So we get down to working problems. We'll get through a lot of problems. And if you don't get enough problems out of this chapter, at the end of this chapter, we'll go back to the McVeigh book, and we'll do some problems out of it. If you don't like that, we'll do some more, we'll do some more, we'll do some more until we're all comfortable doing this, then we'll have a test. What? A test, yes. A test on this stuff. Okay, well, that's fair.
Comes after this.
Not much. This is the high point. This is the, what do you want to call it? The worst or the best or whatever you want to call it. This is the part that scares people. This is the part that makes everybody cringe. But then you get over it. You say, okay, I can do that. And you go on. There are other things that you can do. There's a little bit with Fourier transforms, but finding the variables in Fourier transforms is a bear, and I don't think we need to do that. You need to understand that a Fourier transform can give you certain pieces of information, which is a valid thing to know. But to be able to solve a Fourier transform and be able to analyze it and find all of those constants is not important. It can be done. I don't think we're going to try. I don't remember if we are, and Bode plots, but everybody's done Bode plots and they're not hard. That's not a big deal. But this is the, okay, I've said it enough. My wife says, you've already said that 3 times. We'll say it again. No. No, I'll try to not. But anyway, this is the chapter, and we're going to come down here and we're going to start working problems. Okay. Oh yeah, you could do Thevenin and Norton too. There's nothing you can't do with this that there's nothing that you've already done that you can't do with this procedure. This really takes you back to digital, or this really takes you back to your first course, which is your 1010 course, and this is the whatever. So after you learn the special case of AC, then you come back and you learn this. Node analysis. Here's node analysis. And what else? With node analysis, what else do they have? Mesh should be right next. Why is mesh analysis superior to nodal analysis? Messy denominators. So anyway, I'm scanning this in so that you can have a copy of it if you want it. Here's your mesh. And I would expect you to be able to do this. This is not hard, okay? Two panes, two equations, two unknowns is not hard with this. Three equations, three unknowns gets tacky. But two is not bad. In other words, this would be a two. Two equations, two unknowns. Okay? Two equations, two unknowns is not hard. I would expect you to be able to do this. Three equations, three unknowns, all of a sudden you start asking for help. Three equations, three unknowns isn't bad. Four equations, four unknowns is impossible. So expect a two. I do not want to think about a nodal analysis problem, but I probably will do a mesh analysis problem with you and expect you to be able to do one. Okay? And he gets carried away with where things are at on the complex plane. Yeah, we talk about nodes, or we talk about poles and zeros, but if it's on the left half plane, it's good. If it's on the right half plane, it's bad. That's where you get your e to the plus sign, and that's not good. Anyway, so now we're down to problems in this chapter. Now, I have not reviewed in this chapter what good problems I would assign, but for right now, let's just start, and we won't go too far into chapter 10, but chapter 9, any 15. Any 15. You hand in any 15, you're good. You can even go over and work some problems from that other homework assignment that I just did and count those as some of them. I don't care. I just want to see you working Laplace, taking, doing the conversion process. I want you to be able to look at this sheet as your friend, not your enemy, and be able to do the whatever it takes. Okay, so let's look and see what they're asking to do in 10.1. Again, my apologies. I did not work on this last night. If I would have been working on this last night, I'd have probably said, you can work these problems, don't work these problems. Right now, I'm just shooting from the dark, but I'll just start with 10.1. Okay. Let's look at this circuit and see what they're asking for. I want a Z equivalent, okay? Now here, they just use the values R and 2R and C. And what would be the equivalent of that? Okay, so I've got 2R, I've got C, and I've got 2R over here. Okay, so what would be the value? So what is the resistance of this? 1 over CS, right? Okay, so what would be your response to this? It's 1 over, or it is R1, R2 over R1 plus R2. That's the one I would use in this case, okay? So it would be R1 is equal to 2R plus 1 over CS. R2 is just 2R. So it's this, it's 2R plus 1 over CS times 2R over 2R plus 1 over CS plus 2R. Oh, it's 4r squared plus 2r over cs all over what? 4r plus 1 over cs. So here again, you probably want to get rid of your denominators in the numerator and denominator, multiply this over, so you'd probably say it's 4r squared cs plus 2r over cs over RCS plus 1 over CS. The CS is canceled out, and that's my final answer. I don't know what that means, but that's what I would say for that one. Okay, something like that. That's problem 10.2. It's not 10.1. But that's how I would do that. Basically, just pull your sheet out and answer them what they ask. Okay, and I'm not trying to figure out how they would do this, but I'm just saying, what would be the parallel combination of these two? These are not easy. I'm just going to be blunt with you that these are not easy questions, and I'm not going to try to solve them for you other than all I want you to be able to do is to use what I showed you to find currents and voltages. So this is, they're asking questions here that are kind of above that level, but I'm just going to ask you the simple question. What would be the value of this the parallel combination, and then down here C, and then 2C, or C over 2. C and C over 2. Well, this is R times 2R over 3R plus what? This would be 1 over CS. This would be 2 over CS. So it would be plus R1, R2 would be 1 over CS times 2 over CS all over 3 over CS. So it would be CS would be in the denominator. So this is equal to 2R, 2/3 R plus thirds, and this times 1 over CS. Yeah. So that would be your, this is my resistance. 2R over 3 plus 2 over 3 CS. And they ask, what is that equal to? S equal minus 3. Okay, select the values of R and C to locate a 0 at blah, blah, blah at that point. I don't know. So this would equal to, this is equal to this. So this would equal, so 2R over 3 would equal to 2 over 3 CS at that value. So again, that's not a big deal. I'm not worried about that, but that's how you analyze that. This is how you would analyze this, like based on your sheet, okay? Okay, now moving along, what is the maximum value of poles? Again, I'm not going to worry about that. Find the expression of Z equivalent as a rational function, locate its poles and zeros, blah, 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 select a value to it. So again, they just basically are playing with this stuff. I need real values. Okay, now for number 9. Okay. So here, what do you have? For the circuit, if R equals 560, L equals 2, and C equals 0.5 microfarad, locate the poles and zeros. Okay, so I just basically want you to be able to write the Z for this. What would be the Z equivalent of this circuit right there of 9? Okay. Once you find the Z equivalent, you've got a number. It's a polar number, and that polar number gives you where the poles and zeros are. Okay. If it's in the numerator, it's a 0. If it's in the denominator, it's a pole. Okay. Numerator 0. Numerators, the zeros. Denominators, the pole. Okay. So if they ask you for the poles and the zeros, what are the values in the numerator that goes to 0? What are the values in the denominator that goes to 0? That's how you do that. I don't really need to know that. All I need to know is how you would convert this into a Z. Okay, Z equivalent is what? For number 9. Well, they've got an L. What is it? L, it's an LS. So you got an L, you got an LS. Now an R is just an R. What is the C? 1 over CS, right? So what is my total Z for that circuit? It's LS plus R, R1, R2, R times 1 over CS over 1 plus, excuse me, R plus 1 over CS. All right? And that's it. Now, when they ask for the poles and the zeros, it's where in the numerator this goes to 0 and where the denominator goes to 0. Okay, so let's just expand this out. R is 560, L is 2, C is 0.5 microfarads. So you find all this in one equation. So you've got to reduce this down to something over something, something over something. How do you do that? Well, you just have to start. And R is 560, L is 2, and C equals 0.5 times 10 to the minus 6th. So here is 2S plus 560 over 0.5 times 10 to the minus 6th S all over 560 plus 1 over 0.5 times 10 to the minus 6th S. So how do you get this into one thing? I get this to go all the way across. I just did it a little bit ago. Now it doesn't work. No, I don't want to do it. I don't know. All right, so now I have it a little bit bigger. Heck on it. Can't do it. So I'll just do it like this. Sorry. Okay, so anyway, 2s, so this is equal to 2s times 0.5 times 10 to the minus 6 times s plus 560 all over 0.5 times 10 minus 6s. That's all over, that's the numerator. And then in the denominator, it is 560 times 0.5 times 10 to the minus 6s plus 1 over 0.5 times 10 to the minus 6s. And these go away. So now I have 2s times 0.5 times 10 to the minus 6s plus 560. So I have 2s squared times 0.5 times 10 to the minus 6th plus 560 all over 560 times 0.5 times 10 to the minus 6th s to be 280 times 10 to the minus 6th s plus 1. All right, so where are my poles and my zeros? My poles in this whole thing are at, you have to divide through, so the s is 1. So you'd say s plus something over here. And that's my pole. It'd be 1 over 280 times 10 to the minus 6 in the denominator, or 1 divided by 280 times 10 to the 6th. That's my one pole, and that'd be my pole. And my zeros would be this, and there would be 2 of them, and it would be high. They would be imaginary numbers, would be those 2. These would be my zeros. These would be my poles. But this is how you, this is the expression you would get. That's really all you have to do with that one. Okay? Again. All right, let's bring this back. Okay. I'm getting anxious to get down to the real problems. What I'm trying to do is try to figure out how to do these. I want you to be able to okay, so here it says use voltage division to find V out. Okay. So this is a question where they're asking you to find the Thevenin equivalent of the circuit in the S domain. So they basically are saying, we're going to convert this over. We've converted it over. Now find in the S domain, find Thevenin. That's what they're asking for. So what would be the Thevenin equivalent circuit of that? Well, it's a Vs. So what would be Vs conversion to a Thevenin? Vs over S. Okay? So what would be the value of this? V, what would be the V out? What would be the V out here? No current through that, so what would be V out? It's V out over S times what? 2 over CS over R plus 2 over CS. What is that called? What rule is that? Voltage divider. Use the same rules you've learned before. There it is. Okay? Now, what would be, so my voltage out is this. What would be my Z, or this is equal to V Thevenin in the S domain. What would be my Z Thevenin, or my R Thevenin? It's R plus R parallel with 2 over CS, or it's equal to R plus R times 2 over CS over R plus 2 over CS. Done. That's it. Okay, so here they're actually going to, in 15, they're going to actually ask you to find the value of the circuit. So here you have a choice. It says no, find the of Z Thevenin, and they want you to practice using Thevenin. So how would you do this one? How would you do this one right here? They do the same thing. I need numbers. I need something with numbers. Let's go down and see if they've got something actually with numbers. A lot of this they're just asking you for theoretical values. I want to find some with actual numbers. Okay. So far, it's just all with the variables. Here we go. Now, this one is actually with numbers. So here we are. This is 1035, okay? So it takes all the way to 1035 to find ones that actually have numbers. All right, so let's do 1035. So here we have a circuit with a U, 15 U of T, which is basically what? It's a battery, plus and minus. We've got 10K up here. We've got a 0.22 microfarad capacitor, and we have a resistor. So this is 10K. What would be my Thevenin equivalent to the left of the interface? What would be my Thevenin equivalent? What is V Thevenin? What is Z Thevenin? Okay? In terms of S domain. Okay? What would they be? What would be V Thevenin? It's 15 over S times what? 10K over 10K plus 10K plus what? Over 0.22 times 10 to the minus 6th S. Which is what? Okay, now you got to work. So it's 15 over S times 10K over 20K plus 1 over 0.22 times 10 to the minus 6th S. So now I've got to get this into something that is more meaningful. All right? So I've got to multiply the 20K times the 0.22 times 10 to the minus 6th S. 20K times 0.2 times 0.22 times 10 to the minus 6th s plus 1 over 0.22 times 10 to the minus 6th s. All right, so that's that. Now I've got the denominator is the numerator, so now I've got to flip that up to here. How the heck do I pull this over? I do not know. I'm going to work on that. Okay, so basically at this point in time, I've got to take this value and well, I'll tell you what, I'm going to work on it and I'll get back with you. But this is where we're going to stop. I'll let you work on this one, and we'll come back at this one on Wednesday. Take care. Have a good day.